Hi, we have been discussing the harmonic oscillator problem. We obtained the eigenvalues and eigenkets for the harmonic oscillator Hamiltonian. But we are yet to discuss the time evolution of the oscillator. So in this session, we shall discuss the time development of the oscillator and we shall work in the Heisenberg picture. We shall see how the position and the momentum operators depend on time. We shall also discuss how the expectation values change with time. What we have done so far holds at some instant of time, for example at t equal to 0. And the operators that we talked about, x, p, a and a dagger, they can be regarded either as the Schrodinger picture operators or as the Heisenberg picture operators at t equal to 0. In this session, we shall work exclusively in the Heisenberg picture, which means that x, p, a and a dagger are all time dependent. We shall not write the superscript h because it's a little bit inconvenient to write this everywhere. You just have to remember that we are working with Heisenberg picture operators. One way to describe the time evolution of operators in the Heisenberg picture is to start with the Heisenberg equations of motion. The Heisenberg equation of motion for the momentum operator is dp by dt is equal to 1 divided by ih bar, commutator of p with h. Now you just have to substitute here the harmonic oscillator Hamiltonian, which is p squared divided by 2m plus half m omega square x squared. The only non-zero commutator in here is that of p with half m omega square x squared. You can either evaluate this commutator directly or you can use this formula. The commutator of p with some function of x is equal to minus ih bar, the partial derivative of f with respect to x. And that gives you dp by dt is equal to minus m omega squared x. Okay. Similarly, dx by dt is 1 divided by ih bar multiplying the commutator of x with the harmonic oscillator Hamiltonian. This commutator also can be evaluated easily. The only non-zero commutator here is that of x with p square divided by 2m. You can now either use the formula commutator of x with some function of p is equal to ih bar partial derivative of f with respect to p, which gives dx by dt is equal to p divided by m. You can also evaluate this commutator directly. So what we have here is 1 divided by ih bar, commutator of x with p square divided by 2m. Alright, you can pull this 1 by 2m outside and you have 1 divided by 2m ih bar, the commutator of x with p multiplied by p. Now you can use this formula, commutator of a with bc is equal to commutator of a comma b multiplied by c plus b multiplying commutator of a with c. Remember, in writing this formula, you have to be careful with the order of the operators. It's easy to remember. In here, b comes before c. So in these expressions also, b must come before c. All right, and we have to take all these commutators. You have to take the commutator of a with b, and you have to multiply c from the right here. But when you take the commutator of a with c, you have to multiply this b from the left. Okay. Now using this you get, this becomes 1 divided by 2m ih bar. This is commutator of x comma p multiplying p plus p multiplied by commutator of x with p. Okay, commutator of x with p is ih bar. So this is also ih bar. You get dx by dt is equal to 1 divided by 2m ih bar 2 ih bar p. This ih bar cancels, 2 cancels and you finally get p divided by m. Okay. The Heisenberg equations of motion for p and x form a pair of coupled differential equations. Okay, because the differential equation for p involves an x and the differential equation for x involves a p. But if we move on to the differential equations satisfied by a and a dagger, we'll see that they form a pair of uncoupled differential equations which are easier to solve. You can obtain the differential equation for A by combining these equations in such a way that we obtain the combination A is equal to square root of m omega divided by 2 h bar x plus ip divided by m omega. But it's easier to just find the Heisenberg equation of motion for A, because according to the Heisenberg equation of motion we know that dA by dt is equal to 1 divided by ih bar, the commutator of A with the harmonic oscillator Hamiltonian, which can be written as h bar omega a dagger a plus half. Okay. Now this commutator is easy to evaluate. This is equal to 1 divided by IH bar, commutator of A with H bar omega A dagger A, because the other term is 0. The commutator of A with H bar omega multiplying half, this is 0. Alright. Now this can be written as 1 divided by IH bar. Commutator H bar omega can be pulled out. So we are left with the commutator of A with A dagger A. Alright. This is equal to H bar cancel. So this is equal to omega divided by I, the commutator of A with A dagger multiplying A. There is one more commutator which involves commutator of A with A, which is equal to 0. And we already know that the commutator of A with A dagger is equal to 1. We had evaluated this. So we get dA by dt is equal to omega divided by I multiplying A, or dA by dt is equal to minus I omega multiplying operator A. Alright. Now if you look at this, this differential equation involves only A. There's an A here, there's an A on the right side. Okay. So this is much easier to solve. It's better to work with the differential equation for A and A dagger rather than working with the differential equations for P and X. Alright. Now you can easily find the equation of motion for A dagger either following these steps, or you just take the Hermitian conjugate of this equation on both sides, and you get dA dagger by dt is equal to I omega A dagger. Alright. So we see that this pair of differential equations are a pair of uncoupled differential equations. We can solve them easily. Okay. We now have two simple differential equations to solve. One is dA by dt is equal to minus I omega A, and the other is dA dagger by dt is equal to I omega A dagger. Now these differential equations have simple solutions, as we already know, because here we have derivative of a function gives the same function multiplied by minus I omega. So we immediately know that the solution is of the form A of t is some constant, which would be the constant of integration, multiplying exponential minus I omega t. And this constant itself can be determined by taking the condition t equal to 0. At t equal to 0, this factor is 1, and we get A of 0 is equal to A, which means that the solution for the annihilation operator A of t is equal to A of 0 multiplying exponential minus I omega t. Similarly, A dagger of t has the form A dagger of 0 multiplying exponential I omega t. Alright. Now if you look at this, you see that the number operator and the Hamiltonian must be time independent, because n is equal to A dagger A. But if you multiply A dagger to A, this factor cancels and you have A dagger of 0 multiplying A of 0, which means that the number operator does not depend on time. So the Hamiltonian, which is written as h bar omega n plus half, is also time independent. Now there's nothing surprising in this, because this is something that we already knew. Because if the Hamiltonian has no explicit dependence on time, then in the Heisenberg picture, h of t is equal to exponential I ht divided by h bar, h of 0, and then exponential minus I ht divided by h bar. The h appearing here is evaluated at t equal to 0, which means that these commute, alright, exponential I ht divided by h bar and h of 0 commute. So we should get h of t is equal to h of 0. Okay, and that's exactly what we see here. Okay? From here also we see that the Hamiltonian itself is time independent even in the Heisenberg picture. Okay. From these expressions for A of t and A dagger of t, we can find expressions for x of t and p of t. What we need to do is to use this expression for A and this for A dagger, because A is written in terms of x and p, A dagger is also written in terms of x and p. So if we write out this expression in terms of x and p using this, okay, the left hand side becomes square root of m omega divided by 2 h bar. We are just substituting A by this expression. All right. But A here is evaluated at time t. So we'll have x of t plus ip of t divided by m omega. Okay. And on the right side, we have got A of 0, which is square root of m omega divided by 2 h bar. x of 0 plus I p of 0 divided by m omega. And we also have this exponential minus I omega t here. Okay. And the square root of m omega divided by 2 h bar cancel on both sides, and we get this expression x of t plus I p of t divided by m omega is equal to x of 0 exponential minus I omega t plus I p of 0 divided by m omega multiplying exponential minus I omega t. Okay. Similarly, from this expression for a dagger, we get the relation x of t minus I p of t divided by m omega is equal to x of 0 exponential I omega t minus I p of 0 divided by m omega exponential I omega t. Okay. Instead of a of t and a dagger of t, we now have expressions involving x of t and p of t. We can separately find expressions for x of t and p of t. For this, we expand exponential minus I omega t here in terms of cosine and sine. We know that exponential minus I omega t is cos omega t minus I sine omega t. So substituting that in here, we get x of t plus I p of t divided by m omega is equal to, here we have got x of 0, and this exponential I omega t is cos omega t minus I sin omega t. So it becomes x of 0 cos omega t minus I x of 0 sin omega t. Similarly, the second term here becomes plus I p of 0 divided by m omega cos omega t, all right, plus I p of 0 divided by m omega multiplying minus I sine omega t. Okay. Here, I multiplying minus I gives 1. So this term can simply be written as p of 0 divided by m omega multiplying sine omega t. Okay. Now, we can rearrange a little bit and we can write this as x of 0 cos omega t plus p of 0 divided by m omega sine omega t plus I multiplying, there's an I here and here. Okay, so we can pull that I outside from here and here, and we get I multiplying minus x of 0 sine omega t plus p of 0 divided by m omega cos omega t. All right. Now here we have one Hermitian operator and an anti-Hermitian operator. Whatever is inside this bracket is Hermitian, but when you multiply it with I, it becomes an anti-Hermitian operator. On the left side also you have a Hermitian plus an anti-Hermitian operator. Okay. Now just like we do for complex numbers, we can separate. In the case of complex numbers, we separate real part and imaginary part. In the same way, we can separate the Hermitian part and the anti-Hermitian part. So we write x of t is equal to x of 0 cos omega t plus p of 0 divided by m omega sin omega t. That's what we have here. And from the anti-Hermitian part, we get p of t divided by m omega is equal to minus x of 0 sin omega t plus p of 0 divided by m omega cos omega t. We can multiply on both sides by m omega and we get p of t is equal to minus m omega x of 0 sin omega t plus p of 0 cos omega t. We now have the solutions for x of t and p of t. We have solutions for x and p. We have obtained x as a function of t and p as a function of t, and what we need to know is the initial conditions, x at time t equal to 0 and p at time t equal to 0. So given the operators at t equal to 0, using this we can find the operators at any later time t. Okay. These solutions for the position and momentum operator look the same as the solutions to the harmonic oscillator problem in classical mechanics. So we see that the x and p operators oscillate just like their classical analogues. We obtained the position operator and the momentum operator as functions of time by solving the Heisenberg equations of motion. Let's now look at an alternative derivation of the same results. When we discussed the Heisenberg picture of time evolution, we said that the operator, Heisenberg picture operator at time t is related to Heisenberg picture operator at time t equal to 0 by this relation. A of t is equal to u dagger of t comma 0, A of 0 multiplying u of t comma 0. And in our example, u has the form exponential minus iht divided by h bar. So we can apply this formula directly for the position operator, and then we will have x of t is equal to exponential iht divided by h bar, x of 0 multiplying exponential minus iht divided by h bar. So instead of first constructing the Heisenberg equation of motion and integrating it, we can evaluate x of t directly using this expression. Okay, so the next question is, how do we evaluate this expression? For this, we can use what's called as the Hadamard's formula or Hadamard's lemma. The Hadamard's lemma says that exponential ig lambda a exponential minus ig lambda, where g and a are operators and lambda is some parameter, has the following Taylor series expansion. The first term is a itself. The next term is I lambda multiplying the commutator of g with a. And the next term is I square lambda square divided by 2 factorial multiplying the commutator of g with the commutator of g and a. Okay. The next term, of course, would be I cube lambda cube divided by 3 factorial multiplying the commutator of g with the commutator of g with the commutator of g and a. Okay. And the general term would have this form. Now, before using this lemma, let's try to prove it. There are different ways to prove the Hadamard's formula. One way would be to expand the exponential here and here, carry out the multiplication, and show that the terms are the same as the terms that we wrote down in the expression previously. Let's do it in a slightly different way. We shall consider this as a function of lambda, f of lambda, and then take a Taylor series expansion about lambda equal to 0. We know that for some function f of lambda, the Taylor series expansion about lambda equal to 0 gives f of 0 plus lambda multiplying the derivative of f with respect to lambda evaluated at lambda equal to 0. The next term we know is lambda square divided by 2 factorial multiplying the second derivative of f with respect to lambda, again evaluated at lambda equal to 0 plus etc. Okay. Or compactly we can write it as f of lambda is equal to f of 0 plus lambda f prime of 0 plus lambda square divided by 2 factorial f double prime of 0 plus etc. Here f prime of 0 means df by d lambda at lambda equal to 0. That is, you have to take the derivative of f with respect to lambda and then substitute lambda equal to 0. Okay. Let's now evaluate each term in this Taylor series expansion provided f of lambda has this form. The first term corresponds to f of 0. So we just substitute lambda equal to 0 in here. Here we will have exponential ig multiplying 0. Alright. So this would be the identity operator. Here also you get the identity operator. So f of 0 is equal to a. Let's now find f prime of lambda, which is the derivative with respect to lambda of f of lambda. This was our f of lambda, exponential ig lambda a exponential minus ig lambda. We know how to take this derivative. You just have to use the product rule. First, we take the derivative of exponential ig lambda, that is ig exponential ig lambda, and keep the second term the same, a exponential minus ig lambda. Next, we keep this term the same here, exponential ig lambda, and take the derivative of the second term, that is a minus ig exponential minus ig lambda. We now just have to rearrange the terms here. Let's look at this term. Here we have the operator g and a function of the same operator, g and exponential of g. We know that an operator commutes with itself. An operator commutes with any function of itself. So g and exponential ig lambda commute, we can take, which means that we can take g to this side, right? So the first term I write as I exponential ig lambda, g a exponential minus ig lambda. Over here we have a minus I, which I bring it to this side, and the second term becomes minus I exponential ig lambda, ag exponential minus ig lambda. Now you look at the term, you see that we have I exponential ig lambda here and I exponential ig lambda here as well. Okay, and on the right side also we have exponential minus ig lambda here and exponential minus ig lambda here, which means that we can take this as a common term on the left, I exponential ig lambda. Okay, and exponential minus ig lambda is a common term on the right. Okay, so I have taken I exponential ig lambda here and exponential minus ig lambda over here. And what are we left with? We are left with GA from here minus AG, which is nothing but the commutator of G and A. Okay, so this term can be written as I exponential ig lambda, the commutator of G with A, multiplying exponential minus ig lambda. Okay, so this is the result for f prime of lambda. All right. Now what we need is f prime of lambda evaluated at lambda equal to 0. So we find f prime of 0, which is f prime of 0 is equal to, just put lambda equal to 0 in here. This becomes the identity operator. This also is the identity operator, and we get f prime of 0 is equal to I commutator of G with A. We have f prime of lambda equal to I exponential ig lambda, commutator of G with A, exponential minus ig lambda. Let's now find f double prime of lambda, which is the derivative with respect to lambda of f prime of lambda. We just substitute for f prime of lambda from here. Okay, so we have f double prime of lambda is equal to I derivative with respect to lambda of exponential ig lambda, commutator of G with A, which is some operator, multiplying exponential minus ig lambda. Now if you look at this, this is exactly of this form. All right, earlier we found derivative with respect to lambda of exponential ig lambda, some operator exponential minus ig lambda. And what did we get? We got I exponential ig lambda, commutator of G with whatever operator is appearing here. Okay, multiplying exponential minus ig lambda. What we have is exactly of the same form. Instead of an A here, we have another operator, commutator of G with A. The rest of the reasoning is the same. So this answer should be I multiplied by, right, just following the same steps. Right, or just by looking at this, we see that the result should be, there's an I here, so I multiplying by, there's an exponential ig lambda here, which should appear here also. Okay, and what we have here, this is the commutator of G with whatever operator is appearing here. All right, so the commutator of G with, so instead of A here, what do we have? We have the commutator of G with A. Okay, so this is G comma whatever operator is appearing here, which is the commutator of G with A. All right, and we also have this exponential from here. All right, we also have this exponential minus ig lambda. Okay, exponential minus ig lambda. All right, so f double prime of lambda is now, we already have an I here, and we get an I from this derivative also. So we have I square exponential ig lambda, the commutator of G with the commutator of G and A, multiplying exponential minus ig lambda. Okay. So using the same result, using the result for f prime of lambda, we are able to find also f double prime of lambda. Okay. Now we have f double prime of lambda. We now need to evaluate this at lambda equal to 0. So f double prime of 0 is I square, the commutator of G with the commutator of G and A. We just put lambda equal to 0 in here, and both these become the identity operator. Okay. I leave it as an exercise for you to show that f triple prime of 0 is I cube multiplied by the commutator of G with the commutator of G with the commutator of G and A. Okay. So now we have f of 0 is equal to A, f prime of 0 is equal to I multiplying the commutator of G and A, f double prime of 0 is equal to I square multiplying the commutator of G with this commutator. Okay, and f triple prime of 0 is equal to I cube multiplying the commutator of G with this term, all right, which is commutator of G with the commutator of G and A. All right. Now what we had for f of lambda, the Taylor series expansion for f of lambda, which was about lambda equal to 0, was f of 0 plus lambda multiplying f prime of 0 plus lambda square divided by 2 factorial multiplying f double prime of 0 plus etc. So we put all these things in here. F of 0 is a. So exponential ig lambda a exponential minus ig lambda becomes a plus lambda multiplied by f prime of 0. We have f prime of 0, I multiplying commutator of g with a. So the second term becomes I lambda multiplying commutator of g and a. Here we have got lambda square divided by 2 factorial multiplying f double prime of 0, and f double prime of 0 is I square multiplied by this term. Let me substitute, and the third term becomes this. Alright, and obviously the fourth term will be, you can check this because the pattern is clear. Alright, the first term is a, the second term is I lambda multiplying the commutator of g with this term. Alright, the third term is I square lambda square divided by 2 factorial multiplying the commutator of g with this operator. Okay, so obviously the next term would be I cube lambda cube divided by 3 factorial multiplying the commutator of g with this operator. Okay, so we will have commutator of g with the commutator of g and a in here. Okay, we have just proved the Hadamard's lemma. Now we just have to apply the Hadamard's lemma to this expression for x of t. In place of lambda in our previous expression that we proved, we have a t divided by h bar. So direct application of the Hadamard's lemma gives x of t is equal to x of 0 plus I lambda. Instead of I lambda, we have t divided by h bar. So this becomes I t divided by h bar multiplying the commutator of h with x of 0. Alright, and the next term is I square t square divided by 2 factorial h bar square multiplying the commutator of h with the commutator of h and x of 0. Right, and it goes on like that. Let's now evaluate each of these commutators. First, the commutator of h with x of 0. We can substitute h is equal to p square divided by 2m plus half m omega square x square. When you evaluate the commutator of h with x, the only non-zero contribution comes from this, right? Because the commutator of x with x is 0, right? So this term does not contribute. So this commutator is the commutator of p square divided by 2m with x. You know how to evaluate these commutators, and we get minus ih bar p of 0 divided by m. We will also need the commutator of h with p. Alright, and the Hamiltonian, again, the non-zero contribution comes from half m omega square x square, because there's another term p square divided by 2m. When you calculate the commutator with p, right, this term does not contribute. Evaluating this commutator gives ih bar m omega square x of 0. Let's also find the commutator of h with the commutator of h and x of 0. But the commutator of h and x of 0 we already found to be minus ih bar p of 0 divided by m. So what we need is the commutator of h with minus ih bar p of 0 divided by m. And this is equal to minus ih bar divided by m multiplying the commutator of h with p of 0. And the commutator of h with p of 0 is already found here. It is ih bar m omega square x of 0. So this is minus ih bar divided by m multiplying ih bar m omega square x of 0. The m cancels. Minus I multiplying I gives 1, and we have h bar square omega square x of 0. So the commutator of h with the commutator of h and x of 0 is h bar square omega square x of 0. Right? Let's evaluate one more commutator. And this commutator, this thing we have already found, which is equal to h bar square omega square x of 0 from the previous slide. So this commutator is just commutator of h with h bar square omega square x of 0. Again, we can use the result that we already found for the commutator of h and x of 0. Right? And finally, you get this term, this commutator to be minus ih bar cube omega square divided by m multiplying p of 0. Okay. Now let's put all these together. These are the commutators we obtained. Let's substitute all these into the series expansion for x of t we obtained earlier. The first term is x of 0. We just write it as it is. The second term is IT divided by H bar multiplied by the commutator of H with X. So we write it as IT divided by H bar, and the commutator itself was minus IH bar divided by M multiplying P of 0. Okay, so that's how we get this term here. And here we have I square T square divided by 2 factorial H bar square, okay, which is this term, multiplying this commutator. Okay, and this commutator was H bar square omega square multiplying X of 0. So we get the third term here. For the fourth term, we have got I cube T cube divided by 3 factorial H bar cube, which is this, multiplying this commutator, which is minus IH bar cube omega square divided by M multiplying P of 0. So we just put it in here. Okay, this was just simple substitution. Let's now simplify this further. You see that H bar here cancels, H bar square also cancels here, H bar cube in this term also gets cancelled. And here I multiplied by minus I is 1. So this term is simply T divided by M multiplying P of 0. Okay. And here I square is minus 1. So this becomes minus T square omega square divided by 2 factorial multiplying X of 0. Okay. So we get this term. And here I cube multiplied by minus I is minus I raised to 4, which is minus 1. So this term becomes minus T cube omega square divided by 3 factorial M multiplying P of 0. Okay. We see that some of the terms involve X of 0 and some of the terms involve P of 0. Let's separate them. So the terms involving X of 0 are this, X of 0 and minus T square omega square divided by 2 factorial multiplying X of 0. Alright. So we can pull this X of 0 outside and we are left with 1 minus omega T square divided by 2 factorial, and then there are the higher order terms which we haven't written down here. Alright. And the terms involving P of 0 are this one and this one. Now if you look at this, there's no omega in this term, whereas in this term there is an omega square T cube. It would be nice it was an omega cube here. So we can write this as omega cube divided by omega. And here also we can write this as omega divided by omega. Now let's pull out P of 0 divided by M omega from these terms. Alright, here also we have P of 0 divided by M omega. We pull out this and we are left with omega T minus omega T cube divided by 3 factorial plus etc. Okay. Now you can look it up. These terms in this brackets are the Taylor series expansion or the series expansions for cos omega t. This is the series expansion for cos omega t, and this here is the series expansion for sin omega t. Alright. Of course, you can show that these are the correct series expansion from the expansions for exponential, from the expansions of exponential I omega t and exponential minus I omega t. Because for example, cos omega t can be written as exponential I omega t plus exponential minus I omega t divided by 2. You just use the series expansion here and show that the series expansion for cos omega t reduces to this thing. Similarly, the series expansion for sin omega t is this thing. So finally we have this is equal to X of 0 multiplied by cos omega t. Okay, and this is P of 0 divided by M omega multiplying sin omega t, which is exactly the solution that we had obtained earlier by solving the Heisenberg equations of motion. Okay, we have obtained the expressions for X of t and P of t in two different ways. First, we obtained this by solving the Heisenberg equations of motion, and in the second method, we use Hadamard's lemma to find X of t and P of t directly. We see that the time dependence appearing here are oscillatory because cos omega t and sin omega t are oscillatory functions. Now what about the time dependence of expectation values? At first sight, it may seem that the expectation value of X of t and P of t oscillate with time, right? Oscillate in time with angular frequency omega. but this conclusion is not correct. For example, if the harmonic oscillator is in one of the energy eigenkets, say ket n, then the expectation value of x and p is 0 at any time. Right? So we can write the expectation value of x of t in the state denoted by ket n. Now this is 0 because x of t can be written as a combination of a of t and a dagger of t. Right? It's actually a of t plus a dagger of t multiplied by some constant. Alright. Now a of t acting on ket n takes it to a state ket n minus 1. Right? And a dagger of t acting on ket n takes it to a state ket n plus 1. So when we take the inner product with n here or bar n here, these are going to give values 0 because of orthonormality. This is also obvious from our earlier conclusion that the expectation value of an observable taken with respect to a stationary state does not vary with time. So if the state is an energy eigenstate, then the expectation values do not change with time. Right? The expectation values do not oscillate, they don't even change with time. If you want to observe oscillations of the expectation values, then you must look at a superposition of energy eigenstates. For example, you may consider a state ket alpha is equal to C0 ket 0 plus C1 ket 1. This is a superposition of energy eigenkets ket 0 and ket 1. If the harmonic oscillator is in this state, then we can show that the expectation values of x of t and p of t do oscillate. The expectation value of x of t in the state ket alpha is written as bra alpha x of t ket alpha, and ket alpha itself was C0 ket 0 plus C1 ket 1, which means that bra alpha is bra 0 C0 star plus bra 1 C1 star, and x of t itself was found to be x of 0 cos omega t plus p of 0 divided by m sin omega t. Putting all these together, the expectation value for x of t in the state ket alpha can be written in this form. Right? What we have here is bra alpha, this is ket alpha, and this is x of t. Okay. Now we have to expand this, and we see that some of the terms are going to be 0 because the terms involving bra 0, x of 0 and ket 0, this is going to give 0 because x involves a and a dagger, and it will take ket 0 to other state ket 1, or it will annihilate this state. In both cases, this combination is going to give 0. Alright. Similarly, this combination is also going to give 0. Bra 1 C1 star x of 0 cos omega t C1 ket 1. This is also going to give 0. So the non-zero terms are the cross terms. Alright, so let's write down the non-zero terms alone, and we get there are 4 non-zero terms. There is bra 0, x of 0, cos omega t, and then involving ket 1, alright, involving C1 ket 1. That's the first term here. Alright, then we also have a term from here, bra 1 C1 star x of 0 cos omega t and C0 ket 0. Right? So these are the two terms written here. Similarly, we also get two non-zero terms from here. Bra 1 C1 star C0 ket 1, okay, and bra 0 C0 star P of 0 divided by m sin omega t multiplying C1 ket 1. All these are the 4 terms that are non-zero. So here I have written down only the non-zero terms. Let me not go into the details of the steps. You can try this by yourself. And in the end, you get C0 star C1 cos omega t, bra 0 x of 0 ket 1, C1 star C0 cos omega t, bra 1 x of 0 ket 0, it's x of 0 here. Alright. And similarly, there's a term involving bra 0 p of 0 ket 1 and bra 1 p of 0 ket 0. These are the 4 non-zero terms. We can evaluate each of these using the expressions for x of 0 and p of 0 in terms of a of 0 and a dagger of 0. For example, consider the term bra 0 x of 0 ket 1. You just use x is equal to square root of h bar divided by 2m omega a plus a dagger. Alright, this part can be pulled out of the inner product, so that's why we have it here, and then we are left with the calculation of bra 0 A plus A dagger ket 1. Okay. Now again, A acting on ket 1 gives ket 0, and from this term we get a non-zero contribution, which is square root of h bar divided by 2 m omega. Okay. Whereas this combination bra 0 A dagger ket 1 gives 0, because A dagger acting on ket 1 is square root of 2 multiplying ket 2, and by orthogonality this term is 0. Okay, this is 0. Similarly, you can calculate all other terms using the corresponding expressions for x and p in terms of A and A dagger. You may check the steps of this calculation and let me know if there are any mistakes in them. Anyway, the result I got for the expectation value of x in the state ket alpha is square root of h bar divided by 2 m omega multiplying c0 star c1 plus c1 star c0 cos omega t plus I square root of h bar omega divided by 2m c1 star c0 minus c0 star c1 multiplying sin omega t. Now, as expected, we see that the expectation value, the expression for the expectation value, has oscillatory terms in it. So the expectation value of x of t and p of t have oscillatory terms in them if we consider a state ket alpha, which is a superposition of energy eigenkets. Okay, C0 ket 0 plus C1 ket 1, for example. But these oscillations look very different from the oscillations of a classical mechanical particle in a harmonic oscillator potential. So we may ask if there are states in quantum mechanics which oscillate just like a classical mechanical particle in a harmonic oscillator potential. And the answer is yes. There are these states called coherent states. Okay, and the wave functions or the wave packets corresponding to the coherent states can be shown to oscillate just like a classical mechanical particle. We shall discuss more about coherent states in our next class. Let me conclude for now. Thank you.